Now the question is, what accounts for the stability? Why aromatic compounds are more stable than anti-aromatic compounds? Although, if we look at both the structures in here, both are cyclic and both are planar, but it all comes to the number of electrons to decide if the structure is stable or if it is not stable. Now, in order to explain why do we need the number of electrons and why the number of electrons is important to determine the stability of the structure, we have to consider the molecular orbitals of the cycle. Let's have this example over here. So let's say if you have a benzene and you're asked to prove by inscribed polygon method that benzene is aromatic. I know that benzene is planar and I know that benzene is cyclic, but I want to prove using its number of electrons and the molecular orbitals of the benzene that benzene is aromatic. So to do this, first of all, I need to know how many pi molecular orbitals does the benzene have. And the rule says that the number of pi molecular orbitals is equal to the number of p atomic orbitals. So this is the first thing that you would need to figure out. How many pi molecular orbitals does the benzene have so that you can draw them? Count your number of p orbitals. So I have 1, 2, 3, 4, 5, and 6 p orbitals in there. Remember that every double bond is a 2p orbital. So this is why I have 6p orbitals here. So you have 6p orbitals implies you have 6 pi molecular orbitals. Now, to draw the 6 pi molecular orbitals, the first thing that you do is you draw your cycle and make sure that one carbon of the cycle is pointing down. So this carbon over here is pointing down. Okay? Then you go ahead and you cut your cycle in half. And this is called a diagonal line. So you cut it in half in there. And then once you cut it in half, you're going to end up having 3 carbons in this case. 3 carbons are going to lie under the line. These are going to be called the bonding molecular orbitals. And you're going to end up having 3 carbons above the line. And these are called anti-bonding molecular orbitals. Now the line that we just drew, we're going to call it a non-bonding line. And this line over here lies the non-bonding molecular orbitals in it. And then you are going to go ahead and draw a circle around your cycle in there. This is why we call it an inscribed polygon method, because your polygon, which is the cycle, is inscribed in a circle. Now the carbons or the points where your carbons intersect with the circle, these are your molecular orbitals in there. So these are my 3 molecular orbitals up, and these are my 3 molecular orbitals down. To name those molecular orbitals, you just give them 1, 2, 3 for the bonding and the star for the anti-bonding. So you have pi 1, and then you have pi 2, and then you have pi 3. And all of those are bonding molecular orbitals. Remember that for every bonding, there's an anti-bonding in there. So for pi 1, you have a pi 6 star as an anti-bonding. For pi 2, you have a pi 4 star. And for pi 3, you have a pi 5 star in there. So these are now your 6 molecular orbitals, your 6 pi molecular orbitals in there. Pi 2 and pi 3, they lie in the same line, so this is why they have the same energy. Pi 1 is a lower energy than pi 2 and pi 3. And the way that we fill our electrons in the molecular orbital, you fill them from the bottom to the top in there. Make sure that if you have molecular orbitals of the same energy, Fill one at a time. Fill one electron at a time for each one of them. Don't fill one to the max and then go to the other. So here I do have, count your number of electrons in the benzene, and it's 1, 2, 3, 4, 5, 6. So this is going to be 6 pi electrons. So I have a 6 pi electron in there. So now let's go ahead and fill those 6 pi electrons. So we're going to start with pi 1, and pi 1 we're going to fill it to the max with 2 electrons. And then I'm going to have an electron in pi 2 and an electron in pi 3. This is how I fill it, because pi 2 and pi 3, they do have the same energy. And then I go with another electron with pi 2 and another electron with pi 3, and now I'm done with the 6 pi electrons. Then we're going to go ahead and look at the highest occupied molecular orbital. And here in this case, pi 2 and pi 3 are both our highest occupied molecular orbital. These are the highest orbitals that are filled with electrons. And then we're going to prove, using the highest occupied molecular orbitals, why our structure is aromatic. So you look at the highest occupied molecular orbital and see, and if your highest occupied molecular orbital is completely filled, then in this case, your compound is going to be a diamagnetic, and your compound is going to be aromatic, stable. And if your highest occupied molecular orbital is partially filled, then in this case, your compound is going to be paramagnetic, and it's going to be anti-aromatic or non-aromatic. It depends if your compound is conjugated or not. Let's have these two examples in here. We want to prove, using the inscribed polygon method, the stability of these compounds. Are these compounds stable or not? So are they stable or not? We're going to prove using the inscribed polygon method. So in order to do this, you need to draw the molecular orbitals of the cycle. So let's start with the cyclopropene cation. The compound is cyclic. It is planar. The cycle has 3 p atomic orbitals. Each double bond is a 2p atomic orbital, and this carbon over here has an empty p atomic orbital because it is a carbocation. All of these carbons are sp2 hybridization, all of them. So it's a 3p atomic orbital, implies it's a 3 pi molecular orbital. The number of electrons is a 2 pi electron. After figuring out your p atomic orbitals, your pi molecular orbitals, the number of electrons, we're going to draw the molecular orbitals of the structure. To do this, make sure that one of the carbons of the cycle needs always to be pointed down. Okay? And then go ahead and draw a line that cuts the cycle in half. That line is going to be the non-bonding line. Underneath this line, you have the bonding molecular orbitals. Above the line, you have the anti-bonding molecular orbitals in there. And then go ahead and inscribe your cycle in a circle. The points where your cycle, your carbons meet the circle, these are the molecular orbitals in there. So you have the 3 molecular orbitals, the 3 pi molecular orbitals. This is going to be pi 1, this is going to be pi 2, and that is going to be pi 3. And all of those are stars in there because they are anti-bonding. Now I'm going to go ahead and fill the number of electrons. I do have 2 pi electrons only. So my pi 1 is going to have 2 electrons. My highest occupied molecular orbital here, this one is completely filled. Because it is completely filled, this means that the structure is going to be aromatic. Okay, this is very important when you inscribe your cycle in a circle. Make sure that one of the vertices is pointing down. This means that you cannot draw your cycle like this in a circle. You cannot do this. So you cannot say these are the three molecular orbitals in there. This is not right because it's always that one of the vertices needs to be pointed down for every single cycle. Same thing for the cyclobutadiene. Here I do have, it's cyclic, it's planar. It does have 4p atomic orbitals. That is going to make it having 4 pi molecular orbitals in there. And the number of electrons is a 4 pi electrons. So in order to draw your cyclobutadiene, in this case, inscribed in a circle, as we said before, you would need to make one of the vertices of the cycle pointing down, and that is going to force you to make your cycle like that. So your cycle is going to be like that, and now you inscribe it in a circle. You're gonna draw a line that cuts the cycle in half. This makes that these two molecular orbitals here, if you inscribe it in a circle, then these two molecular orbitals, they are going to lie on the non-bonding line. You have your bonding molecular orbital and your anti-bonding molecular orbital. So this one is going to be pi 1. And all of those, I'm just going to go ahead and give them a star. So it's going to be pi 2 star. This is going to be pi 3 star. And that is going to be pi 4 star in this case. Okay, I do have my 4 pi electrons. So that is going to be 1, 2. This is going to be 3. This is going to be 4. And then you stop. You look at your highest occupied molecular orbital. And that is not completely filled. This is going to be not completely filled. And because it is not completely filled, that is going to make it a paramagnetic. Paramagnetic means that it is not stable. And this is why, because it is not stable, it's going to be an anti-aromatic. Make sure that it is planar though. So this one is cyclic, it is planar, this is why it's an anti-aromatic. If it was non-planar, then in this case it will be non-aromatic, so pay attention to that. We can use aromaticity in order to predict the acidity of the compound. So let's have these three structures in there. The rule says that you always look at your structure and make its conjugate base and a check. If the conjugate base is stable, then its acid is strong. So let's start with the first one, the cyclopentadiene. Take one hydrogen out, make its conjugate base. That conjugate base is cyclic, is planar, is conjugated, so it is aromatic. Do the same thing for the other structure in there. This is cyclic, planar, conjugated. Number of electrons is 8, so this one is anti-aromatic. We know that aromatic is more stable than anti-aromatic. So that is going to make this structure over here to be more acidic. Its acid is going to be more acidic. Structure over here to be more acidic than the cycloheptadiene. Benzene is not an acid. Benzene is a nucleophile. It is electron rich because of the conjugation of its p orbitals. So the hydrogens of the benzene in there, they are never ever acidic. Benzene is going to be a base. It is a weak Lewis base in there, and it can never be an acid. So this is going to be the trend of the acidity for these three structures. In this chapter, we will consider the reactions on the benzylic carbon only. In the next chapter, we will consider the reactions on the benzene. So benzylic carbons, if they have hydrogens, they do undergo oxidation. Here I'm using a strong oxidizing agent. Since they have hydrogens, then each carbon is going to turn into a carboxylic acid. It doesn't matter how many carbons you have. Okay. Let's say, for example, if I have these three substituents around the benzene, always locate your benzylic carbon and check if the benzylic carbon has a hydrogen. If they have a hydrogen, then these carbons are going to get oxidized into a carboxylic acid. It doesn't matter how many carbons you have in the chain. We only care about the benzylic carbon, and that benzylic carbon will turn into a carboxylic acid. The rest of the chain will be oxidized further into carbon dioxide, but you don't have to mention that. Oxidation always happens on the benzylic carbon, and you need to have a benzylic hydrogen. If there's no benzylic hydrogen, and as in the case of the tertiary butyl group, then there's nothing is going to happen to the tertiary butyl group and no oxidation will happen.